Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the awesome stuff. This is part of the good stuff. This is the AAS Journal Author Series. And I am very, very happy to have Elisabeth Adams with us today. Hello, Elisabeth.
Hello.
And who is our fuzzy friend with us today?
This is Saffron. She sits in on all my Zoom calls. I was present when this whole paper was written and during much of the research.
Good color for that. Very cool. Very cool. Well, Saffron, I expect you to repeat this when we're done. So very good. And you got some very lovely pictures over your head there, Elisabeth. What are those?
So my daughter made those for me last year. She's 7. I guess 6 when she made them. So that's our solar system. So you got the sun and then the planets in order. That's Ceres.
Oh,
and then if you look back this way, you got Pluto and Charon and the Kuiper belt, and way over there is Eris and Sedna.
very good. Very cool. Very cool.
That's what happens when you're the daughter of a planetary scientist.
Guilty. Very nice. And it is September 24th, 2024, as we record this, post-equinox. So we're into autumn. And Elisabeth, what's your geolocation?
I'm in Boston area.
Okay. And as fall started, are the trees starting to go?
There's a hint of yellow. It's still, what it's doing is it's no longer hot.
There we go.
It's pleasant.
There we go. And I will say the same thing. I'm here in Phoenix, and we have definitely hit coming out of our late summer, and we're into early fall. So the big temperatures are done, we hope, cross fingers. So yeah, cooling off a little bit. It's very nice. And Elisabeth, what do you like to do for research?
Well, so I like to look at transiting extrasolar planets. I particularly like the really short period ones. This is what I've been working on for off and on for most of my career, frankly.
Very good.
This paper has a special spot in my heart because I published some of my thesis data that never made it into a published paper before. So this is only 14 years later.
It happens sometimes. Very cool. Very cool. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Doomed Worlds 1. No new evidence for orbital decay in a long-term survey of 43 ultra-hot Jupiters. And Elisabeth, take us away.
All right. So I'm going to plug our research group. It's the Short Period Planet Group, or Super Pig if you kind of smush it together. We just made stickers. I think I'll have them at DPS if any of you are there.
Oh, I will be at DPS, but I'm going to have you show that. I'm going to show you that sticker at the end so I get a better shot of it.
Yes. We also have some little 3D printed pigs that my collaborator Brian Jackson made. So this is work that I've been Brian Jackson and I have been the instigators of Super Pig, which has been in existence for about a decade now. We started up because the original Kepler survey didn't look for planets with periods of orbital periods of less than a day. Yeah. And it turns out there are some.
Cool.
And so some of my other collaborators on here are Amanda Sikafus in South Africa, who's done a lot of observing for me. Jeff Morgenthaler he's in Maine. His telescope's in Arizona and is a roboticized telescope. So he looks at Jupiter and I look at exoplanets. And then Hannah Waters is also in South Africa. We have a number of students on this paper. Haley and Dallin are at Boise State, and Saki's at Queensland in Australia, and Stein-de-Kaiser is also at Cleveland. We took some observations on the Minerva telescope, and Chelsea Huang there. And Nevin Weinberg is our resident theorist to help us with.
Token theorist there. Yeah, very good. Okay, awesome. Good shout out. Good shout out. Okay.
All right. So the goal of this project is to look for orbital decay. And since I want to say it was 2017 is when WASP-12b was published with a decreasing period that was best explained by the orbital period actually decreasing due to tidal decay. Okay. If you attempt to measure a transit, if you're looking at observations of transits and you see that the timing of the transits is not strictly regular, you can learn all sorts of interesting things about the system. If it oscillates, there could be another body in the system. If the period is increasing, It could also mean there's some three-body interactions or some weird cases of tidal decay that I don't fully understand. Talk to our theorists.
Okay.
And it could also, but if you see decreasing orbital periods, that could be due to tides from the star causing the planet to decay.
Right.
And the planets we're looking at are ultra-hot Jupiters with periods of a few days.
Okay.
And the orbital period is important. That's how we identify them. But what really matters is how close the planet is to the star and how massive it is.
Yes. Okay.
In particular, these are my favorite planets because you can draw them to scale. Like, so the star's over here and the planet is right here, and that's actually scale, like both sizes and separations. They're crazy close. So what happens when you stick Jupiter right next to its the sun? Well, you get some massive tides. The star raises tides on the planet raises some tides on the star, which are less important. And the orbital, like the planet's structure shifts, but also the planet's orbit can start to change. And due to a lot of complicated theoretical, I'm not gonna talk about the theoretical reasons for why you get orbital decay. That's a whole other paper. But the short answer about that is that there has been a lot of modeling work to try to explain stellar tides and the ranges of timescales over which this can happen, which is parameterized by this value Q star prime, has many orders of magnitude, ranging from 10 to the 5 to 10 to the 10, depending on which particular model you're looking at.
Yes.
And importantly, the one planet we detected it for, WASP-12b, has a Q of 10 to the 5.
Okay.
So is that typical? Did we find that one because it's the weirdo that is decaying super fast? Or are we, is there a wide range? Like, do these planets, do all stars have the same Q star? We actually think they shouldn't because
different masses and
different masses, but also different stellar structure. So where you have convective layers in the star matters. And we also think that it can depend on exactly where the planet is in its orbit. It will experience different tides at different points in its orbital journey because it's at different periods. And there can be a frequency dependent decay rate. So it gets very complicated, and that is why we have Nevin and other theorists around to do the calculations. But I'm interested in the opposite side. Like, I want to just see if we can detect orbital decay, and then let the theorist figure out if it's too fast or too slow or just right.
Right. Goldilocks.
That's right. So we can go to the next page.
Sure. Just to put it up, we know about 100 of them.
Yep. All right. So I said that so if we go scroll down to the middle of the next page, WASP-12b is the planet that we've known about for the longest, that has had multiple observations, and people have observed not just the transits of the planet, but also the occultations, or the secondary eclipse where the planet crosses behind the star. If you can time when that happens, if the planet's orbit is really decaying, then they should both be decreasing.
Right.
If the planet is precessing and has a slightly elliptical orbit, then the occultations will be increasing while the transit times decrease, and vice versa. They sort of slosh back and forth.
Cool. I'm with you.
Okay, so WASP-12b, people have detected pretty firm evidence for it. And then there's been a whole wash. You can see all these different planets that people are detecting hints of possible orbital decay. I think there's a dozen planets that I've listed here. And some of these planets, we think that I should properly say hints of orbital period decrease, because some planets have had measured rates that are much too fast to be orbital decay. And it could be due to the motion of the star. That's the case, we think, for WASP-4b.
Okay.
And maybe Trace 5b. There's a couple ones where people have investigated, but WASP-4b is the only one that I'm aware of actually somebody running the numbers. You have to take radial velocity measurements and see and detecting the motion of the star and saying this is about the right amount to account for most of the timing effect that we see.
Okay.
And then many of these other ones are just based on timing, transit timing, and getting a small preference for an orbital decay model. And then what do you do with that information?
Yeah.
And the answer is you write a paper with 43 different planets in it, trying to go through and assess everything. And I'm going to just back up for a moment and say that this paper talks about 43 planets because that's the observations we had when I first started prepping this for submission a year ago. But
Right.
we only do a deep dive into my top 6.
Okay.
Because there's only so many. This beast came in at 28 pages, I think. So there's only so
Yeah.
we're working on more papers to fill out the rest of them.
I look forward to another 29 pager. Yeah.
No, the plan is to have more than one paper and have a few planets per paper.
A little smaller bite sizes. Okay.
More bite sized. That's right.
Okay. Very cool. I'm with you.
Okay, so the way you tell the difference between the models is this thing, it's our equation 1, if you scroll to the bottom, that's the Bayesian information criterion.
Mm-hmm.
And that penalizes the model for having extra terms because you can always fit more terms to a model and come up with an amazing, perfect model that just fits your data beautifully. But
yes,
the simpler model is better if the simpler model can explain it. So you calculate the BIC value for a linear ephemeris, no period change, and then a changing period ephemeris.
Okay.
And then you compare them, and that's equation 5. That's the delta BIC value, where you just subtract the two. The bigger your delta BIC value is, the bigger the preference.
Okay, 3, 4, and I'm with you.
For that model.
5.
Yes.
There we go.
So the equations 2 through 4 are just walking you through how do you calculate a transit ephemeris.
Yeah.
So the simplest way to calculate a transit ephemeris is you have a reference midtime and a period, and then you just count the number of orbits or epochs it's been since your reference time, and there you go. You have your predicted transit time.
Okay.
But maybe you need to add on a quadratic term, that's equation 3, and that quadratic term can be either positive or negative, depending on if the period is increasing or decreasing.
Right. Okay.
And so we are looking for both. Both are interesting. Only one of them is the planet's decaying, but
absolutely.
I'd be happy to find positively increasing planetary periods too.
Those are interesting. Yes. Okay.
And then equation 4 is just keeping track of the gory math, because a lot of this business is being very careful with your units and
yes. Okay.
properly converting things. Okay.
Okay.
So we are looking at
sure
43 planets. Why don't we dive into some data? That's the next page.
Let's take a look at some of the data. These things.
We took a lot of new observations. We combed through the literature for existing observations, and in some cases had to comb back to the original sources for a lot of papers. And then we also used test data and Corot data and combined everything together to come up with a more uniform approach for each of these systems.
Nice. Good.
All right, so I'll just briefly jump through our telescopes. We've got IOIO, which is a 35 centimeter robotic telescope in Arizona that was built to look for volcanoes on Io.
Very
but
cool.
Jupiter's only up about half the year, so the telescope gets bored. And Jeff and I figured out how to make the telescope be less bored by observing exoplanets the other half of the year.
Very cool.
And then we also have access to a 40-inch telescope in South Africa. It's going to become a 2-inch telescope now, because the 40 inch is getting recommissioned. And so we've taken, you go to figure 1, you can see some of the many, many light curves.
Okay, let's zoom out a little bit. You get kind of a global here. T in flux. Okay.
And so these light curves, well, they range from beautiful and exquisite to okay in data quality, and that's kind of what you expect when your telescopes are ranging from, well, actually, I think I have some data in here from, this is some of my unpublished thesis data that I mentioned too. So if you see the ones that say Morris, those are from the IRTF, which is a 3.5 meter telescope in Hawaii. And those from 2009 and 2008 or from long ago, but we finally published them.
All good. It's all good.
And as you can tell, 3.5-meter telescopes take amazing data. It
Mhm.
depends also on the brightness of the star, how great it is. But what you get
Two more.
is you get a nice dip, and you can time the mid-time. You can time when that dip happens pretty well, even if it's sort of crummy data. Like some of those IOIO light curves are not great, but we know approximately when the mid-time is with some more error. And that's the thing about the transit timing business for a long-term effect like orbital decay is it takes at least a decade to find it, and maybe 20 or 30 or 50 years, depending on how slowly it's happening. So you are going to be stitching together data from telescopes for a long time if you want to detect this.
Right. There any issues with that? Imagine
Yes.
so.
Oh, there are issues. We will get to the issues in just a minute.
Okay.
Let's keep it positive for right now before we dive into the weeds.
It's still positive. Okay. Very good.
They're not insoluble issues, but they require some careful
Sure.
record keeping that
Yeah.
for those of you who are out there in the audience, publish your original light curves, please.
Yes. Yes. That make a note to the editors as well.
Yes, this is actually my plea to the editors too, is it is my personal opinion that you should not accept transit light curve papers for publication unless they publish their original light curves.
I will pass that one along.
If everybody had been doing this since my thesis, 15 years ago, we'd be in a much better place.
Yep.
They weren't.
Fortunately, data sharing has gotten a lot more prevalent.
Sure, I know, and they're just text files. Like they're not that to archive for posterity. I don't need the original light curves to go remake the data.
Yeah. Okay.
Okay, so we've got these beautiful light curves. I think we could skip ahead. Table 1 just tells you the details of when and where all these light curves were taken, and you can go read the paper if you really care, but it's they come from all over the world, and they span 15 years in time, and there's 6 different planets that we've taken new data for, and then we've combined them with hundreds of light curves from other sources.
Yes.
So let's see. Oh yes, I talk a little bit more about Minerva Australis. That's the Australian telescope we took a transit with, and then the IRTF and Las Campanas. That's right. I also have some data from Las Campanas in here too. That's a 6.5-meter telescope. So from 0.3 meters to 6.5 meters, we have spanned the gamut of data.
Very good. Very cool.
And let us not forget TESS. TESS is an amazing resource, the transiting exoplanet space satellite, because it observes these planets regularly. So most planets have 1 or 2 or 3 sectors of TESS data at this point. And TESS will go observe it. Sometimes you'll get 2 sectors in a row, and then it'll come back 2 years later because TESS looks at the northern hemisphere, then it looks at the southern hemisphere, and then it switches. So every other year you'll come back to the same planet, unless you fall in a gap in the silicon, which is true for a couple of them, or if you fall in the continuous viewing zone. There are a few planets that they have lots of transits of. This is great, but most planets do not fall in the continuous viewing zone. And if you go every 2 years, and TESS data only goes back to 2018.
Yeah, something like that.
2019. It's been a while, but it hasn't been that long. So we can't detect orbital decay with just TESS data alone.
Okay.
We need to get data from elsewhere. And also, who knows how long TESS is going to go in the future? May it live 1,000 years. But
may it live. 1,000 years.
Well,
you're an optimist. You're an
million years.
Very good. Okay.
All right, and then finally, the last source of data I did was I went and downloaded for CRO 2b, the CRO photometry, which CRO was the first, before Kepler. There was CRO.
Yes.
Observing transits from space, and there aren't very many planets that are in the CRO data, but for the ones that you have, it's a lovely, lovely source of historical data from 2007, 2008, which gives you so much baseline for detecting CRO data. All right. Cool. Where do I want to go to from now? We could talk a little bit about the literature light curves. So here's the thing with the literature light curves. They're all over the map. So if you want to try to figure out who has observed a particular planet before, there isn't really a good way to do that. Like you can't, there's a website called the Exoplanet Transit Database that's maintained by a Czech volunteer group and is amazing and is also undergoing, this is my plug for it, it's undergoing a rehaul to their system right now. In a few weeks, they're going to go live with a new and improved version. But it mostly has been used by amateur astronomers, which is also amazing because they are observing light curves when the professionals do not have time and research money to do so. And so we've relied heavily on their light curves to fill in critical gaps.
Very cool.
But there isn't a professional equivalent of this. NASA's Exoplanet Archive does not archive transit midtimes. So you need to identify, there have been papers that have compiled them, but mostly what people do is they compile all of the light curves for their particular paper, they dump it in a table and publish it, and then somebody else will go and use that compiled table and then add a few more light curves in the next iteration. So if there's a mistake in the first paper or the first compilation paper, it just gets propagated through. And if you are the poor grad student whose job it is to go compile 100 light curves from 15 different sources, you may misread. And I say grad student here, but I also mean senior research scientists make this mistake too. It is quite possible to misread the caption on the figure in the 15th paper you look at and just not actually get the correct timing system. Because we need to talk a little bit about timing. To time and the transit midtimes accurately, you need to be using a barycentric dynamical time. So you need to adjust for the light travel time across our solar system. We ignore light travel time in the exoplanetary solar system because these things are all happening at transit, which is the same phase. Like they're always at the same spot in their orbit. So we can just, and they're also extremely close to their star, so they are not that far. It's not that big a difference. And so we can ignore, but in our solar system, there's 16 light minutes between Earth on one side of the sun and Earth on the other side of the sun, which is a lot. And so people report dates in the UT time system that their computers observe them in, and then you need to find the coordinates of the observatory and correct them to the barycenter of the solar system. People have also corrected to the heliocenter of the solar system, which is not precisely the same thing. It's within a few seconds, which is fine for transits, but most people, but the tools that people have been using to convert between these two timing systems means that the barycentric Julian days are typically reported in the TDB timing scale, which has corrected for leap seconds, and heliocentric Julian days are typically not reported in that. So there's, at this point, it's about 60 or 69 seconds difference between these. So if your times are off by about a minute, that is a suspicion that somebody messed up their conversion error. And people will publish, unfortunately, people will sometimes publish dates that are in BJD UTC and just write them as BJD, and then will later misinterpret them as BJD. It's just
know that coordinate
system.
Know that coordinate systems and clocks.
Know the coordinate systems. I'm just going to plug Jason Eastman wrote this paper in 2009, 2010. I forget the exact year on it, about how to achieve better than 1 minute timing accuracy on exoplanet transits. And it was all about how you absolutely need to keep your coordinate systems correct. And fortunately, it's almost guaranteed that when you dive into a particular system, somebody somewhere probably messed it up because it's just too easy to do. During full disclosure, while I was writing this paper, I found 2 separate cases where I had messed it up in my own code and then had to go back and correct it. It's just, you have to triple check and then check again and then have somebody else check for you.
Someone else.
This would all be much better if you could have if people could do the checking once and then make a database and have all of the transit light curves in the database. You could at least trust the literature times.
Good.
That's my plug for the future.
Good.
Okay, so literature light curves took up a lot of time trying to curate them. If we look at, this is table 3. The important thing, if you zoom in on the end where it says observations, and then there's that thing that says NTR, that's the number of transits. And so that tells you how many transits we have in the database. Like these are the transits that we actually use, not the ones that I discarded because I didn't like their data quality. So there's, I think some of the smaller systems have 8 or, 15 like transits per planet, but many of these other ones have hundreds.
Hundreds, yeah.
So there's about 5,000 light curves, I think, published in this paper.
Cool. Very nice.
And we have data that goes back. The record holder here is WASP 18b, which has 32 years worth of data because somebody went and found some data in a transit that was 10 years before the planet was found originally.
Wow.
So, and then at the small end, we've got some planets that have only been known for 3 or 4 years because they're babies that Tess found. And
yes, or babies to us. Yes.
So we have a huge range of planets available for us.
Yes, the planet.
All right.
Very good.
So what am I talking about next?
And the mass of the planet here is Jupiter masses, yeah?
These are Jupiter mass planets.
Okay.
And then that's stellar and stellar masses relative to the sun. There's also a wide range of stellar types here. This is one of the goals of this project, ultimately, is to see if we can find any trends in, orbital decay rates with stellar sizes. There's a good reason to think that smaller stars have higher Q values, so lower slower rates of decay. We also think that older stars get puffier.
Yes.
And that changes the stellar structure, and that changes their
absolutely will change the dissipation factor. Absolutely.
That's right. So and then there's another part about the age, which is that there has been some independent work. This is Hammer and Schleifman from a couple years ago, that says that ultra-hot Jupiters, or hot Jupiters in general, tend to be around younger stars than general planet-hosting stars.
Sure.
Interpretation being that something happens to them before, like, they leave the main sequence. That, they get evaporated or destroyed somehow. So these are all like pieces in a puzzle that we are trying to put together.
And then you got the interesting case here at Quatar 1b, which is 11 gigayears. That's pretty good. Pretty good age.
Yeah, Quatar 1b is a big one. I don't think I had very many transits of this planet when I wrote this paper. Also, it appears to be not doing very much. Well, let's skip ahead to find actually talk about the data and results.
Okay.
I'm going to skip the next. Oh yes, there's some gory details in here if you'd like to read them about how to account for multiple transit times that are at the same epoch, because some of them are repeats. They're, and sometimes there were 3 different telescopes looking at the same planet at the same time.
Right.
And you want to keep them in. So there's just some cautionary tales about finding examples of duplicates in the literature and
just the general cleaning procedure of coordinate systems and timing.
Yes. And then the other place that errors come into the literature is with composite transit times. So remember from equation 2, I think, which was the linear equation, where you have the transit, you got your reference ephemeris midtime.
Yes.
And your period. So the way you get a reference ephemeris midtime is you take a whole bunch of transits for the new planet that you've just discovered.
Okay.
And then you fit a model to it, and then you'll get a value for that midtime. That is not a midtime of any particular planet. It's the reference midtime, but it's the number that people will often quote in papers because people will publish a table. People don't always publish individual transit light curve timing. They will publish a time for the system. If you want to know when the transits are happening again, you want the best one to predict the future. And if you want to judge variation, you need to know each individual transit.
Individual ones. Yep.
Right. So, but you need to be very careful if you use those reference midtimes as if they were individual transit light curves. They look like they're very, very precise because they're combining, sometimes 10 or 20 transits worth of data and compressing it on a single point. And that will distort your models later, as we will see in one of these later figures.
Okay. Nice. Very good.
All right.
Okay.
And then I've got tables. I have so many tables of data in this paper. If you would like to go dive into the system yourself and go find my errors. I'm sure there's something in there.
Easter egg hunt. Easter egg hunt. Very good.
Uh,
Good. Timing system. BJD TBD.
yep.
Good. 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 Good.
Timing
Yeah,
system
well, it's significantly
and then
good.
also the source from where these times came from. I'm going to give a shout out to Ivshina and Wynn, which is the timing paper that I worked with. It was published
Yep.
in 2022. They compiled hundreds of planets, and it was a very helpful work, even though there are mistakes in that work because you can't compile 400 planets and thousands of light curves
Without error.
without making some mistakes. It's just
Yeah.
not possible.
I'd be guilty. Absolutely.
All right.
Very good.
And here's some more talking about timing systems, which
Well, it's
uh,
super important.
yeah, there's an XKCD comic strip about timing systems that I didn't insert into my paper.
Ooh. That would have been a very, very unusual one. Let's put it that way.
Yes. Oh, all right. So let's jump to figure 2.
Let's go to figure 2. More words on cautions of timing. I hope people got that message at this point.
Caution of timing. Please go read it. Your timing system really matters, and the people who did it 10 years ago may have been using different tools than you did. All right. So figure 2 is where we took the delta Bic values, if you remember from earlier, where we're trying to figure out the preference. Like, is this planet better explained by a linear model or a quadratic model?
Yep.
So for these particular plots, if it is positive, it wants a quadratic model. And if it's blue, it wants a decreasing period model, which is the one that we're looking for with timing decay.
Negative
If
P.
it's red in this plot, it wants an increasing period.
Yes.
Which is not orbital decay, but it's still something interesting. And the short answer, if you look at the top plot, that's just me plotting all these values at once. You can see that WASP 12b has definitely got a decreasing orbital period. And most of the other planets are just not that significant compared to WASP 12b. So I zoomed in the second panel, just zoomed in.
Okay.
And there's a few.
Okay.
There isn't a really good threshold for when you should publish, like when you should trust the delta Bic value. And this paper was sort of trying to explore that. And I think somewhere between 10 and 30 is where it starts to become interesting.
Okay.
Anything below about 10 is really possibly just noise, like it's interesting, but check back later with more data. And once you get above 30, like there's definitely something happening in the data, although whether that's actually an effect or just, something weird in the data is an interesting question. And this bottom panel is where I did this experiment where I tried to rescale the error bars. It's for logistical reasons, we didn't actually refit the transit light curves of all the data. Because as I mentioned, there are over 5,000 light curves in this paper, and they're over 5,000 midtimes in this paper. And I did not have light curves for most of those midtimes, mostly just have tables of data.
Yeah.
I wouldn't actually mind refitting all of them, but it's just currently not possible to do that because a lot of this data has been, let's not say lost. Some of it's been lost though.
It's sort of like a renormalization. Right?
Yeah. So this is like renormalizing. Basically, all the numbers decrease in significance a lot. And any effect that survives is probably reasonably significant. The ones that are still pretty low are probably not that significant. But as you can see, most of the planets disappear in terms of their effect.
Yep.
So that could mean that the error bars in the original times they're underestimated. People use a million different ways to fit their transit light curves, and some groups have just smaller error bars than other people. Like they don't account for all the different sources of noises. And I don't know. So this is sort of your way of trying to decide which of these are robust signals that you should follow up on.
Right.
We make these. I have an updated version of this plot that I'm using to try to guide our future observations.
Cool. Good.
But all these ones over here with nominal effects are ones that we should keep looking at because maybe their delta Bic of 10 will become larger and
fun. Right. Very cool.
Okay. The one thing you don't notice on this paper is, you notice how I said that there were 6 planets in this paper that we were focusing on, but there's only 4 that are above the delta Bic of 30 cutoff.
30, 1, 2, 3, 4. Yep.
This is not my first version of this paper of this plot. This is version, I don't know,
30,000.
20 of this plot. The first version had 6 planets over here.
Okay.
And I'm going to talk about the two of those planets first. So WASP 19b was the first one. All right. Let me just, before I dive into WASP 19b, let's pause on figure 3 and show you WASP 12b so you can see what the data that we're looking at looks like.
Okay.
Let's start with the case that actually works.
Okay. Yep. That one had a really strong.
All right. So this is what it looks like. You have a quadratic effect, and it looks like the datas are low both early and the midtimes are low both early and late. And there's scatter off of it. You can tell individual points are high or low. And I think that one test time is clearly a partial transit that has very large error bars. But even with a fair amount of scatter, our WASP 12b data for this paper was taken with our 35 centimeter telescope and was not very high quality, but if you get enough of it clustered together, like it follows the trend for exactly where it should be. And you can see that the delta Bic value in the second panel increases over time and keeps going up monotonically, which is fairly important. Like the longer time goes on, the more significance we build up for this detection.
Yep.
The third plot is a really important one that you'll see for later things, which is where we calculate the effect on delta Bic of any individual point. And so if any one of these points causes delta Bic to change by a lot, it's going to get highlighted red, which doesn't happen for WASP 12b.
Right.
Points have already been.
It's a fair warning for what's coming.
Yes. And then the bottom panel is it's the observed minus calculated ephemeris if you had a quadratic. Meaning changing orbital period. And as you can see, the bottom panel matches the data a lot better than that black line in the top panel, which would be if it was a non-changing ephemeris. So this is what we want to find. Right. And now we're going to look at these plots for other systems. So we're going to, if we move down to WASP 19b, this is figure 4. I made 2 versions so you can see. Okay, so this was in my first version. Well, an earlier version of that plot. WASP 19b had the next most significant value of delta Bic. I think its delta Bic value is over 200, which is pretty impressive. And you can see, like, the first thing you notice is it's nowhere near as clean as WASP 12b. There's a lot of scatter and noise. Yeah, but you can kind of, think, okay, maybe some of those early times are a little low. But then the next thing you should notice is those red dots above the line. And you can see them in the third panel. There's several red dots that are highlighted. Yes. There's actually 6 transits in that. They're all from the same paper. These are transits that were taken on Magellan, and they were very, very precisely timed. So the more precise their timing is, the more it has an anchoring effect on your model. Yes. So if your mid-time says it within 5 seconds, this was the transit time, then delta Bic's like, okay, that's a really huge result. Like, I believe you, but the delta Bic is not, quite smart enough to
pick that out, to
actually detect this. So those particular light curves, I ended up just discarding from this paper. I figured out how to correct them. Like, it seems like a delta Bic error. I mean, not a delta Bic error. Seems like a BJD time conversion error, but I did correspond with the author, and we couldn't figure it out. But the times are off by about a minute.
That's a lot.
It's suspicious. Well, a minute is also the BJD TDB conversion error.
Yeah, I'll border that.
Which is super smoking gun, but it's a complete unsolved mystery. You notice a couple of other yellow points there. If you look at the yellow points on the left, that's a separate paper that had a conversion. It had a conversion error in the original paper. So Table 2 had the times as they measured it, and Table 4 had the times converted to the HJD system, which is what everybody else used. But the conversion had been done wrong.
Oops.
So I didn't notice that one at first because I just used Table 2 and converted them myself. But once those points have been, once we corrected all of these errors in the literature, and then I think there's a couple other points here that were, there was a typo in a database. Having corrected all of that data, we made the next version of this plot, which is figure 5.
Go down.
Modified literature data. So I fixed 2.
And here we go. Modified literature.
And you may notice that your delta Bic now is negative. There
Ooh,
is
yes.
the effect completely vanished. It was only dependent on those two papers.
Wow. Okay.
So,
Wow.
and this is a cautionary tale
Indeed.
of why it pays to dig into all of the references. And WASP 19b had a lot of references that I had to look into, but it was worth it because didn't want to publish detection of orbital decay of something because that was actually a typo in your database.
Yeah. Very good. Very
So,
good.
so
Okay.
that's the forensic thing. All right, Crow 2b. That's figure 6. I'm just
Okay.
slow it down. I could have made a before and after one for that one too,
19.
but I didn't. So the important thing to look at for Crow 2b is that section of blue data. That is the Crow literature data.
Mm-hmm.
The original version of this plot used a paper that had analyzed. So when the Crow mission was first presented as results, it did not publish all 80 transits as individual light mid times. It just had one time for the whole Crow mission.
Okay.
And then somebody 5 years ago published a paper that analyzed them all.
Okay.
However, I think what happened in that paper is that although they published them saying that they were BJD times, I think they actually published the raw times.
Okay.
But when I went, and because those points had a huge effect. If you just removed the Crow data, the effect went away entirely.
Okay.
I'm like, but the Crow data is beautiful. We don't need to remove it. We should be able to figure this one out. So I went back, downloaded the latest version of the Crow data and refit it, and this plot just popped out.
Down.
And the blue times are right where we expect them to be with all of the other data in there. If you look, there's a couple of blue points right next to it, which are my thesis points, which will ratify where they're
Right there. Yeah.
And so if you plot the difference in times between the Crow data that I refit and the data that was published in the previous paper, it's off by exactly the amount of the BJD correction at that time.
Okay.
So I suspect they just got the wrong column in the data file when they published.
Okay. Oops. Okay.
All right. So Crow 2b also not doing anything.
Good.
Now we're going to move on to a couple of cases of increasing orbital period, but also here's WASP 121. Panel 3 is the one to look at.
Oh boy.
Because there's that first point. If you look at that first point, the delta Bic value drops from it's about 40 to below 0.
Right. This one right here, this red one.
And so that first point is a composite time. Was from the discovery paper. It's an ephemeris. It's their ephemeris time combining. I don't remember the exact number, but all of the available light curves that to date, and they put it into a single reference mid time.
Yeah.
The reason it's on this plot is because we don't have that data. That data was never actually published. There are no light curves available. There's some plots of the individual light curves, and that is the only record in the scientific literature of this data. So it's here because I would love to be able to find that data. I've tried corresponding with the author and have not actually had any success in locating them because people leave the field, I guess, sometimes.
On some hard drive somewhere, someplace. Okay.
Hopefully it's someplace. If anybody knows where the early WASP 121 data is, please contact me.
You get in touch.
Because that particular data point's I'm not saying that that timing is necessarily wrong. The error bars are definitely wrong. And I suspect that once you turn that point into a cloud of data with errors, that it will not be as large an effect. But if it is an increasing period, that is an interesting thing to find. And we would love to detect that.
I'm pulling it away.
All right. So that's WASP 121. Next one's WASP 46.
Okay.
WASP 46 also has a nominally increasing period, although you'll notice it looked like it was a very strong effect, and the delta Bic has been falling the longer time goes on.
Yikes.
And you'll also notice all of those red points for the first 4 or 5 years of observations.
Okay.
So I looked into this one. I couldn't find any smoking guns with that data. There was no obvious BJD conversion errors, but it's possible that there's something wrong. The timing data is so much more scattered in the first 5 years than in the last, 10 years.
Yeah. Yep.
So this is another case where there's a nominal detection that I don't really believe, but I don't really know the whole story of this one. So need some more investigation, and also just to keep monitoring this one in the future and see if the timing trend. Fortunately, this one has test data. That's what the green lines are highlighting, test data.
Okay. Yep.
So the test data has been occurring at a very rock steady times every couple of years.
Indeed.
So I suspect this is another one that's just a data artifact.
Okay.
All right. And then there's Trace 1b. I think this is the last one of the 6 that I was focusing on. Trace 1b is interesting. It's got a slight slope to it.
A little bit.
Probably I should have zoomed in on this plot a little bit more and made the figure. I'm sorry.
Which one? The top
You
one?
find when you look at your published pictures. I should have just rescaled it to see the curvature a little bit better. So it's got it has a decent delta-Bic value of about 70, and I've cleaned up any particular database errors and duplicates that there might have been. The problem with Trace 1b is not necessarily the detection of a changing orbital period. It's that we don't think it can be orbital decay.
Okay.
Because it's just too fast.
Okay.
This corresponds to a Q star value of 10 to the 2.
Okay.
That's what planets have.
Yeah.
Stars do not have Q stars of 10 to the 2.
Usually. Okay.
Yes. So I don't know what the story behind Trace 1b is.
That one remains a mystery. Okay.
It is a mystery. So
okay.
I know other groups have been looking at the system, and I hope somebody can come up with a way of resolving this one. What you need to do is take occultation timing measurements to see what those are doing. If this is a case of orbital precession, then the transits would be doing this and the occultations would be doing this.
Right. Okay.
Trace 1b, as the name suggests, has been known for a long time. But so someone look at those transit data from like 2003 and 2004. Yep. So, and I know there are early occultations. This paper got big enough without looking into occultation timing.
Oh yeah, no, right. A whole nother.
And if you think it's bad trying to extract timing for transit light curves in the literature, try extracting timing from occultation light curves.
Oh, lovely.
They tend to be, they're 10 times shallower depths, and they're people tend to stack multiple ones together because they're trying to detect the temperature of the planet.
Yep.
And they don't care about the timing within a couple minutes. And so the timing they publish, so you'll get a plot that has been phase folded and it just doesn't have the timing information you need anymore. So we're investigating ways to get around this.
Okay, very good.
Okay. And the last one I'm showing is a planet that I did not observe, but I think is really cool. This is figure 10. Kepler 1658b is the other plausible candidate for orbital decay. It was Kepler's first planet candidate, but because at first they thought that it was identified as a false positive pretty quickly, because they didn't realize that the star was a subgiant. So it is a giant planet around a large star. The star is 2 or 3 stellar radii. And once they figured that out, it got a planet designation and they detected the mass of this thing. But it's also got a planetary depth of about 0.1%.
Yikes.
It's not something my 35 centimeter telescope is doing. It's something the 6.5 meter telescope can do. If you look at the right, those couple points over there's a couple of points from Palomar, which is a 5 meter telescope. But you need to have a pet 5 to 10 meter telescope to observe this thing.
Everyone would love a pet 5, 10
Who
meter.
wouldn't love to have a pet giant telescope that you could devote to all of your planets? So this is each sector of Kepler data has one time where they stacked all the data together, and then each sector of test data on the right, plus a couple of ground-based observations. And so this was me just using the time that had been published with no new data just to see what I came up with, and it's a pretty good candidate. It's, delta Bic is 50. There's the only point has a strong effect. I wouldn't call that one an outlier in this plot because it's the most recent point on the plot.
Okay.
And when you have a sparse plot like this, you would expect the points at the beginning and the end to have a big effect.
Yeah.
when there's not that much data overall.
Okay.
So this is an interesting system to watch for sure. For those of you with 5 to 10 meter telescopes at your disposal.
Or otherwise.
Or otherwise, yes. I think, and tests should be re-observing it pretty soon, so we can another data point.
Okay, good. Well, that'll be good.
All right. Table 6 has my best ephemerides. These are both a linear and a quadratic ephemeris for each of the 6 planets that I dove into about, whether their period is nominally increasing or decreasing or staying the same.
Constant. Oh, you got 2 of each. Oh, how fascinating. Okay.
And the fun thing about this is to look at the lifetime of the planets. So WASP-12b has about 3 million years left at this current rate of orbital decay. Of course, the theorists like to complicate everything. There's no particular reason to think that Q star is constant over the whole range. So it is quite possible that Q star will increase or decrease as the planet gets closer to the star and moves into a different regime. So these are all, approximate estimated lifetimes. Actual stars will do something else, whatever the star chooses.
But it is at this point in
yes
evolution. That's what we're getting. Okay,
that's what we got.
For the positive one, sigma. Okay, that's a sigma.
Right. Okay. And then there's a whole bunch of text catching up to what I've been telling you about the figures. So we can skip ahead a bit.
Okay.
We can skip to section 6.8, where I talk a little bit about the marginal systems, because this paper is about
which was most of
systems, not just 6. And the reason it's about the other 43 is I think it's starting to be interesting. So we took 43 planets and we found signs of orbital decay in 6 of them.
Yes.
2 of which were, signs of, or period change, I should say, in 6 of them. 2 of which we checked the literature and found out those were mistakes.
Okay.
But 4 out of 43. So the other ones are the other ones they just need more data to become interesting? Or are they actually meaningfully non-detections? So this is where I'm diving into some of the ones that are marginal detections.
Right.
And noting a few systems that people should look at for the future, particularly ones that other people have claimed minor detections for. The short answer is there's a few that are sort of interesting, but we don't really, I guess I've got Trace 3, WASP-52, WASP-164b, and WASP-32b are all interesting and should be monitored in the future.
Okay, there's a shout out to do. Very cool.
Okay. But all right, so my population analysis is like, okay, so where is everybody? Why is it just WASP-12b?
Maybe they're all gone.
If you go to the next, how do I want to talk about this? That table's a long wall of text. What I want to talk about is the next table, which is table 8.
Table 8. So
table 8 is could we have detected WASP-12b in this system?
Yes.
Phrased 2 different ways, either as if the system had the same Q star, would we have found it? Or if it had the same change of period in milliseconds per year, would we have found it? So I did 2 separate tests. Okay. And WASP-12b mercifully shows up as, yes, we would have detected WASP-12b in the WASP-12b system. The value I used for WASP-12b was the literature reference from the paper I was working with at the beginning. So it's great. We could have detected the one that's actually orbitally decaying. Yeah. Several of these other ones would have had huge values of delta Bic if they had WASP-12b like decay. Like WASP-43 and WASP-19b and WASP-18b would have had, and that Trace 3 all would have been over 1,000. Yeah. Like we would have seen these things if they were decaying. They are not decaying as fast as WASP-12b by at least an order of magnitude or 2. And then there's a bunch more that we would have started to see them looking interesting on my plots. Yep. We didn't. Like none of these systems on here have a detection. If you look carefully at the observed delta Bic, okay, that's not quite true. Trace 3b has a delta Bic of 20, which is the starting to look interesting, but it's still very different than 1,000, which is what it would have been. Right. And WASP-121, remember, That's a 37, their delta pick of 37, but that's for an increasing period, and we are looking for a decreasing period. So it's the exact opposite way. So so this brought us to the question of like, well, what does this say about the Q star of these stars, number one? And what does it say about the population of hot Jupiters in general and WASP 12b's status as a weirdo?
Okay.
So you could empirically measure what a lower limit on Q star if you have a non-detection of orbital decay. Because if Q star were, bigger than bigger than a certain value, you would have detected it.
You would have seen it, right? So right. Okay, I'm with you.
And so that is why don't we go to the figure, because everybody loves figures. This is figure 11.
There's our Q star in case somebody's interesting. dp/dt, mass ratios, distance ratios.
Yes. Yeah. Right. Oh yes. Sorry. Let me talk back up to Q star. This is the equation 6.
Okay.
Yep. Sorry. I'm going too fast.
It's okay. It's all good.
So Q star depends on constants, the rate of change of the planet orbital period over time. It depends on mass of the planet relative to the mass of the star, and it depends on the separation. So A is the semi-major axis, and compared to the
radius of the star.
Radius of the star.
Right.
So this is where having a bigger star and planets matter. And that's a power of exponent of -5. So like the distance really has a strong effect.
Indeed.
On the Q star you measure. So using that number, since we've now measured everything in that equation using our observations, we can go plot it up in figure 11.
Let's go to figure 11. Look at some Q's. Q's. Okay. Ooh, wow.
And so it's a little bit of a busy plot. So what you can see is that the open circles are the nominal detections, and most of these are not significant. They're like 1 sigma detections, but I'll tell you what the nominal value is anyways. The two blue ones are WASP 12b and Trace 1b, which are the two that we detected a decreasing period significally for.
Yes,
and those are filled circles.
Here we go. Right here and right here. Yes.
And then the little purple, the red triangles are the lower limit that was placed on the nominal detection. You'll notice I've got a few lower limits that were placed even though I don't have a nominal detection. That's where it had a nominal positive rate of change, but it's like a +1 sigma. So if you subtract 3 sigma, it becomes, you can get a negative value that you would have detected period of decay of at least this large, and you did not. So the value for Q star has to be at least that red triangle. And it may well go upward. That's why the triangle's pointing up.
Very good. Very good.
The only one I couldn't place that constraint on is WASP 121b, because that had a significant detection of a positive transit.
Right here. Yep.
Because that's the one that has that 1 point at the beginning. There
we go. Okay.
And so then Nevin Weinberg wrote a paper earlier this year where he was using his theoretical model to calculate what we think stars should be doing based on our best understanding of nonlinear dissipative modeling, which go read his paper, get him on the show. I'm not gonna talk about that here.
Fine.
And so he has these purple plus signs. The ones that are 10 to the 10 are a little bit placeholders. Like, we don't think there is orbital decay happening meaningfully on these ones. 10 to the 10 Q is very high up there. But a lot of the planets in our sample, he found could be having Q values between 10 to the, this is done in steps of a half. So like 10 to the 5.5 to 10 to the 7.
Yes. Okay.
And the interesting thing is if you zoom in on the right-hand part of the plot, you can start seeing places where the observed lower limit is higher than the calculated theoretical value.
Yes.
I think it's WASP 19b is where there's a factor of 10 difference between the theorist's best guess and what we actually saw.
Lower limit. Yep. 19B. Right.
So
Yep.
this part right here is where this is the thing I love most about observations, is where we can actually, the theorists could come up with their models and we have our observations and now they are clashing and meeting and going to make each other better as soon as we figure out what's happening. It's
always good to have that comparison, even when it's negative, because it's what you iterate on, right?
And the other thing to notice is the huge range in values.
Oh, yeah.
So WASP 12b is that dashed line and the blue dot, and that's 10 to the 5, slightly more than 10 to the 5. And we already have a lower limit of 10 to the 6.5 for WASP 18b, which is an order of magnitude and a half. 18B. And actually, the one I didn't plot on here because it's not my data, was Kepler 1658b, which is down at 10 to the 4, because that's a subgiant star and has faster decay. Okay. So you can see that there's actually, that's like 3 orders of magnitude between 10 to the 4 and 10 to the 7 almost.
Yep.
Between those stars in our system. So the short answer is, yeah, there's a wide range of values between the stars. So we don't yet know which stars are going to go where. I mean, the theorists have some ideas, but the theorists have not quite figured this puzzle out yet. Just like the observers have not quite. Just like the observers.
So hey,
there's a lot that we still don't quite understand.
Very good. Beautiful.
All right. Yep. Okay. And I'm going to need to, I've got another 10 or 15 minutes and then I need to.
Okay. It's all good. So I think we've probably covered it. You've hit on the, has a database problem. We've covered that.
Yeah. Very
cool.
So we want to talk a little bit about the future.
Okay, so let's wait on until we get there 1 second. So first of all, thank you so much, Elisabeth, for walking us through your very lovely PhD article. Very nice. And since you hinted at it there, and you did mention it a couple of times, let me ask, where do you think we go from here, given the published article? Is there community-wide marching orders to improve their databases? Are there additional observations coming through? Maybe there's another mission coming on that could be useful, Plato, for example. And is there additional theoretical work to be done? So just sort of
yes, and yes.
Okay, where do we go? What's important?
All right, it's all important. So the short answer is about half of these planets we couldn't even find WASP 12b data in. We just need to keep observing them.
Okay.
We've only known about a lot of these planets for 5 or 10 years. So my group, the super pig.
Yeah, put that super pig up. Yeah, there we go.
There we go. Go to the cat. Is working on taking more observations. Obviously, we encourage everybody to observe systems as they can. I recently got a grant funded to do a literature deep dive to start dealing with the archive problem, with the goal of taking 100 systems, fixing their transit midtimes, and then getting this data into the exoplanet transit database so that you can go have a one-stop spot to get your transit midtimes from and to refer back to, so you're not tracing it through 5 different compilation papers and just, at the mercy of all the terrible things that creep in when you do that.
Very cool. Very cool.
And then we are also, TESS is going to keep taking data on these systems, which are the ones that it's observing, which is great. And Plato will be awesome when it launches.
When it gets there.
So, and then the short answer is we need to have a little bit of a long-term view about this, because it could take another 10 or 20 years, particularly for many of these systems. I mean, any given system could be detectable in about 10 years of data, like WASP 12b, or and Kepler 1658b was the same. But the other systems could, we will need to figure out as a community how to deal with light curves spanning 30 or 40 years, because we're heading there really soon. And that means that journals please, please, please require transit light curves to be published. They're text files. They're cheap. You can publish them in the paper. You can put them on Zenodo or someplace.
Or data behind the figure.
Right. You can define the data behind the figure. You can write to the NASA Exoplanet Archive. You can host your light curve there directly as part of the Exoplanet follow-on project. They've got places for observers to post light curves. Like, it would be great to have a centralized repository for light curves as well as midtimes, because we need to refit light curves together as new data analysis techniques are developed.
Yeah. Cool. Well, that's going to be very exciting. It kind of reminds me of proper motion surveys back when you had to wait a while before you got something, right?
Yeah.
So we're kind of that here, but it's very cool.
The neat thing is, even though we're not finding orbital decay around planets, we're still learning a lot of stuff about the stars. And it's like, and there's always the chance that the next one you look at might, like, this might be the season of data that you actually detected in.
Absolutely.
If you don't, that tells us, you know, stars are funny things.
Good thing there's many of them. Very cool. Very cool. Well, I certainly look forward to seeing this field develop over the next year or decade, as the case may be, but it'll be very exciting. It's very nice. Yeah. Elisabeth, thank you so much again for walking us through your very lovely hot Jupiter hunts. Very nice.
Thank you. It's been fun.
Yeah. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. We will see you on the next one. Bye-bye.
All right. Take care.